Welcome! In today's session, we'll explore LeetCode problem number 1216, valid palindrome 3. This problem challenges us to determine if a string can be turned into a palindrome by removing at most k characters. We'll break it down step by step and discuss the key approaches to solve it efficiently. Let's dive in. In this problem, we are given a string s and an integer k, and our goal is to determine whether it is possible to transform the string into a palindrome by removing at most k characters. A palindrome, as you may know, is a string that reads the same forward and backward. For example, the string radar is a palindrome because it is symmetric. The input consists of the string s, which only includes lowercase English letters, and the integer k, which can range from 0 to the length of s. The output is a Boolean value, true if the transformation is possible within the given constraints, and false otherwise. Now, let's take a look at a few examples to better understand the problem. In the first example, we have the string s equal to abcdca and k equal to 2. The output is true, and here's why. By removing the characters b and e from the string, we are left with actka, which is a palindrome. Notice that we have removed exactly 2 characters, which is within the allowed limit of k. This means the transformation is possible, and we return true. On the other hand, let's consider another example where s is a, b, c, d, f and k is 1. In this case, the output is false. The reason for the output being false in the second example is that it is not possible to transform the string a, b, c, d, f into a palindrome by removing just one character. Any single character removed from this string will still leave us with a sequence that is not symmetric. For instance, removing a would result in b, c, d, e, f, which is clearly not a palindrome. Therefore, we can conclude that the transformation is not feasible, and the output is false. Now, in a third example, we have s equal to 8 and k equal to 4. This time, the output is true. Here's why the output is true in the third example. By removing the characters of b, b, and c, the string becomes cc, which is a palindrome. Since we removed exactly 4 characters, which matches the value of k, the transformation is valid. Now, let's consider some constraints and edge cases. The string s can have a length between 1 and 1000, and it only contains lowercase English letters. The value of k is guaranteed to be between 0 and the length of s. For edge cases, if k is 0, the string must already be a palindrome to return true. If k equals the length of s, we can always remove all characters to form a palindrome. Additionally, strings with repeated characters may require fewer removals compared to those with unique characters. To solve this problem efficiently, we can use dynamic programming to find the minimum number of deletions required to make the string a palindrome. If this number is less than or equal to k, we return true, otherwise, we return false. To solve problem number 1216, valid palindrome 3, the goal is to determine if a string can be transformed into a palindrome by removing at most k characters. One way to approach this is through brute force. The idea is to generate all possible substrings of the input string after removing up to k characters and then check each for being a palindrome. While this approach is intuitive, it becomes computationally expensive as the string length increases. The number of subsets grows exponentially, and validating each subset for being a palindrome adds additional overhead. This makes the brute force method impractical for larger inputs. A more efficient solution involves dynamic programming, specifically by finding the longest palindromic subsequence, or LPS. Here, the core insight is that if the length of the LPS is at least nk, where n is the length of the string, then the string can be transformed into a palindrome. To compute the LPS, we use a dynamic programming table. When 2 characters match, we include them in the LPS and add 2 to the result of the subproblem for the remaining substring. If the characters don't match, we take the maximum result by excluding 1 character at a time. This approach significantly reduces the number of redundant computations compared to brute force. Dynamic programming is implemented by defining a table dp, I, j, where each cell stores the length of the LPS for the substring starting at index I and ending at index j. The base cases are straightforward. A single character is always a palindrome of length 1, and an empty substring has an LPS length of 0. The algorithm then fills the table iteratively for all possible substrings, using the relationships discussed earlier. While this approach has a time complexity of O(n squared) as we process an nxn table, it also requires O(n squared) space to store the table. To reduce memory usage, we can optimize the space complexity to O(n) by storing only the current and previous rows of the table. This rolling array technique allows us to compute the LPS iteratively without needing the entire table in memory. The trade-off here is that while the optimized version is more memory efficient, it may be slightly harder to implement or debug compared to the straightforward dynamic programming approach. Despite this, both versions maintain the same O(n squared) time complexity, making them much faster and more scalable than the brute force solution. The key insight here is that the problem can be reframed as finding the LPS and checking whether the difference between the string length and the LPS is less than or equal to k. This reformulation leverages the symmetrical nature of palindromes and avoids redundant calculations. By focusing on the LPS, we directly address the core of the problem in an efficient manner. However, there are trade-offs to consider. While the space-optimized dynamic programming approach saves memory, it may add complexity to implementation and debugging. For smaller inputs, the simpler O(n squared) space solution might be sufficient, as the memory savings from optimization are negligible. Ultimately, the dynamic programming approach balances efficiency and clarity, making it the best choice for solving this problem. It avoids the exponential complexity of brute force methods and provides a structured way to determine if the string can be transformed into a valid palindrome within the given constraints. The problem valid palindrome 3 revolves around determining if a given string can be transformed into a palindrome by removing at most k characters. A palindrome, as you may recall, reads the same forwards and backwards. To solve this, the key idea is to find the longest palindromic subsequence, or LPS, of the string. Why? Because if the length of the LPS is at least the length of the string minus k, then removing the non-palindromic parts can achieve the transformation. The solution relies on dynamic programming, where we define the state dp, I, j, to represent the length of the longest palindromic subsequence in the substring s, I, j plus 1. For invalid substrings, like when I greater than j, the value is 0, and single-character substrings, being palindromes themselves, have a value of 1. The transition between states depends on comparing the characters at the ends of the substring. If they match, they contribute to the LPS length, otherwise, we exclude one of the characters and take the maximum from the resulting substrings. When the characters at both ends of the substring match, we include them in the LPS and add 2 to the length of the LPS for the inner substring. This is expressed as dp, I, j, equals dp, I plus 1, j1, plus 2. On the other hand, if the characters do not match, we have to exclude either the leftmost or rightmost character and take the maximum LPS length from the remaining substrings. This is captured by the formula dp, I, j, equals max, dp, I plus 1, j, dp, I, j1. These transitions ensure that we account for all possible ways of forming the longest palindromic subsequence. Next, we define the base cases. For single-character substrings, dp, I, is set to 1, as they are trivially palindromes. For invalid cases, such as when I greater than j, the value is set to 0. To compute the LPS for the entire string, we use a bottom-up approach, filling the dp table iteratively. We start with smaller substrings and gradually build up to longer ones. Specifically, we iterate over all possible substring lengths, then for each length, calculate dp, I, j, for all valid starting indices I and ending indices j within the string. The nested loops ensure we systematically compute all states. To determine the final result, we look at the value stored in dp, 0, and 1, which represents the length of the longest palindromic subsequence for the entire string. If this value is greater than or equal to any k, we return true, as the string can be transformed into a palindrome by removing at most k characters. Otherwise, we return false. This approach is built on a few critical insights. First, the minimum number of deletions required to make a string a palindrome is equal to the difference between the string's length and its LPS. If this difference is less than or equal to k, the transformation is feasible. Dynamic programming provides an efficient way to compute the LPS by breaking the problem into overlapping subproblems. Additionally, there are some important edge cases to consider. If the string is already a palindrome, its LPS is equal to its length, and the result is always true. If k is greater than or equal to the string length, we can delete the entire string, so the result is also true. However, if k is 0 and the string is not already a palindrome, the result is false, as no deletions are allowed. To implement the solution, we use a 2D DP table of size nxn, where n is the length of the string. This table stores the LPS length for each substring, ensuring we can efficiently compute the result. The space complexity of this approach is O(n squared, due to the size of the table, and the time complexity is also O(n squared, since we iterate over all possible substrings. However, there are ways to optimize the space usage. Instead of using a full 2D table, we can use a rolling array of size n, as each state only depends on the current and previous rows. This reduces the space complexity significantly. Additionally, we can include an early exit condition. If the value of dp, 0, and 1, exceeds nk at any point during the computation, we can terminate early, as the result will definitively be true. These optimizations make the algorithm more efficient while retaining its correctness. Here, we define a class called solution with a method isValidPalindrome that takes in a string s and an integer k. The goal is to determine if it's possible to make the string a palindrome with at most k deletions. First, we calculate the length of the string and then define a helper function called longest_palindromic_subsequence. This function uses dynamic programming to find the length of the longest palindromic subsequence in the string. To do this, we create a 2D DP table where dp, I, j, represents the length of the longest palindromic subsequence in the substring s, I, j plus 1. We initialize the table so that single characters are palindromes of length 1. Then, for substrings of increasing lengths, we fill the table by checking if the characters at the current start and end indices match. If they do, we add 2 to the value from the inner substring, otherwise, we take the maximum value from either excluding the start or the end character. Finally, the function returns the value in dp, 0, and 1, which represents the LPS length for the entire string. Using the helper function, we compute the length of the longest palindromic subsequence, stored in LPS_length. The next step is to check if the number of deletions required to turn the string into a palindrome, which is n LPS_length, is less than or equal to the given limit k. If this condition is satisfied, we return true, meaning the string can be transformed into a palindrome with at most k deletions. Otherwise, we return false. This approach ensures that we efficiently solve the problem by leveraging dynamic programming to compute the longest palindromic subsequence first and then evaluating the deletion condition. Here, we start by defining a class named solution and the method isValidPalindrome, which takes a string s and an integer k as inputs. The goal is to check if the string can be transformed into a palindrome with at most k deletions. To achieve this, we use a helper method called longestPalindromicSubsequence, which calculates the length of the longest palindromic subsequence in the given string. Inside this method, we initialize a 2D array dp to store the results of subproblems, where dp, I, j, represents the length of the longest palindromic subsequence within the substring from index I to j. First, we handle the base case where single characters are palindromes of length 1, so we set dp, I, to 1 for all valid I. Next, we use a nested loop structure to fill the dp table for substrings of length 2 and greater. For each substring, if the characters at the two ends are equal, we extend the palindrome by 2 and add the result of the inner substring. Otherwise, we take the maximum value between excluding the left or right character. This ensures we account for all possible palindromic subsequences in the string. Once the dynamic programming table is fully populated, the value dp, 0, and 1 gives the length of the longest palindromic subsequence in the entire string. We store this result in the variable LPS length. Finally, to determine if the string can become a valid palindrome within k deletions, we calculate the difference between the string's total length n and LPS length. This difference represents the minimum number of deletions needed to turn the string into a palindrome. If this value is less than or equal to k, we return true, otherwise, we return false. This approach ensures that we efficiently solve the problem using dynamic programming, making it both optimal and clear. Here we begin with an example where the input string is ABCDCA and the maximum number of deletions allowed is 2. To solve this, we need to determine if we can make the string a palindrome by removing at most 2 characters. The key insight here is to calculate the longest palindromic subsequence, or LPS for short. Once we know the LPS, the number of deletions required can be calculated as the total length of the string minus the LPS. If this number of deletions is less than or equal to 2, we return true. To achieve this, we use a dynamic programming approach. First, we initialize a 2D DP table of size 7 by 7, as the string has 7 characters. Every cell in this table is initially set to 0. For the base case, we fill the diagonal of the table with 1s because any single character is a palindrome of length 1. This gives us the initial setup needed to begin filling out the DP table for substrings of increasing lengths. Now we focus on filling the DP table for substrings of increasing lengths. For substrings of length 2, we compare adjacent characters. For instance, since it is not equal to b, the value at dp 0, 1 becomes the maximum of dp 1, 1 and dp 0, 0, which is 1. This process is repeated for all pairs of length 2. For longer substrings, say of length 3 or more, we follow the same logic. For example, in the substring BCD, there are no matching characters, so dp 1, 3 is determined as the maximum of dp 2, 3 and dp 1, 2, which is 1. However, for the entire string ABCDCA, the first and last characters match. This means the value at dp 0, 6 will be the value of dp 1, 5 plus 2, giving us 5. By filling the table this way, we eventually construct the final DP table, where the value at dp 0, 6 represents the LPS of the entire string. The completed table shows us how the LPS value increases as we consider longer substrings. Once the DP table is fully constructed, we can compute the LPS and determine the number of deletions required. For the string ABCDCA, the LPS is the value at dp 0, 6, which is 5. The number of deletions required is then calculated as the total length of the string, 7, minus the LPS, which equals 2. Since this number of deletions is less than or equal to the allowed value of k, which is also 2, the result is true. We can validate this approach with another example. Consider the string ABCD where k is 1. The DP table for this string will be initialized as a 4 by 4 table, and we fill it in the same way. The diagonal is set to 1 for the base case, and for substrings of increasing lengths, we compute values based on whether characters match or not. For this string, no matches are found at any length, leading to an LPS of 1. The final DP table for the string ABCD reflects the fact that no characters form a palindromic subsequence longer than 1. The value at dp 0, 3, which represents the LPS of the entire string, is 1. Using this LPS, we calculate the number of deletions required as 4 minus 1, which equals 3. Since 3 is greater than the allowed value of k, which is 1, the result is false. Now, let's look at an even simpler example with the input string AA and k set to 0. The DP table for this string is a 2 by 2 table, and the diagonal is initialized to 1 for the base case. Since the two characters in the string are identical, the value at dp 0, 1 becomes 2, representing the LPS of the entire string. For the string AA, the LPS is the value at dp 0, 1, which is 2. The number of deletions required is calculated as the total length of the string, 2, minus the LPS, which equals 0. Since this number of deletions is less than or equal to the allowed value of k, which is 0, the result is true. This example highlights how the approach works even in the simplest cases, ensuring correctness and efficiency across different scenarios. To analyze the time complexity of the solution, we start by considering the dynamic programming approach used to compute the longest palindromic subsequence, or LPS. The overall complexity is O(n squared, where n represents the length of the input string. This quadratic time complexity primarily comes from the need to fill out a 2D DP table. First, initializing the DP table of size nxn takes O(n squared) time. Then, the core part of the algorithm involves iterating through all possible substrings of the input string to populate this table. The outer loop runs O(n) iterations for the substring lengths, while the inner loop, which iterates through the starting indices of these substrings, also runs up to O(n) iterations for each length. Each individual update to the DP table, such as calculating dp, I, j, is a constant time operation. When you combine these, the nested structure results in O(n) multiplied by O(n), which simplifies to O(n squared). Finally, extracting the LPS length from dp, 0, and 1, is a simple O(1) operation, which doesn't affect the dominant term. Therefore, the overall time complexity remains O(n squared). Now that we've established the time complexity, let's turn to the space complexity. The primary use of space comes from the dp table, which is a 2D data structure of size n×n. This means the memory required to store the table is O(n squared). Additionally, the algorithm uses a constant amount of extra space for variables such as I, j, length, and the result storage, which contributes O(1) to the total space complexity. Since O(n squared) dominates O(1), the overall space complexity is O(n squared). This is an acceptable trade-off, as the algorithm optimizes runtime performance by pre-computing results and storing them in the dp table. While this approach is more memory-intensive than a naive solution without memoization, it's far more efficient in terms of execution time. When comparing this dynamic programming approach to a brute force solution, the improvements become clear. A naive approach would involve generating all possible subsequences of the string, of which there are 2 to the power of n, and then checking each one to see if it's a palindrome. The palindrome check for each subsequence would take O(n) time, resulting in an overall time complexity of O(2 to the power of n*n, which is exponential and highly inefficient for large input strings. In contrast, the dynamic programming solution reduces this to O(n squared by breaking the problem into smaller overlapping subproblems and solving them iteratively. For space, a brute force approach without memoization would only require O(n) space to store the current subsequence. However, the dp solution prioritizes time efficiency over space, using O(n squared) memory to store intermediate results in the table. This trade-off is what allows the dp approach to achieve such dramatic improvements in runtime performance. Furthermore, regardless of the input string, the dp algorithm's complexity remains consistent since the table must always be filled completely based on the string's length. Summarizing the complexities, the dynamic programming solution has a time complexity of O(n squared) and a space complexity of O(n squared). By contrast, the brute force approach has a time complexity of O(2 to the power of n*n and a space complexity of O(n). This comparison highlights the significant advantages of using dynamic programming for this problem. While the space requirement is higher, the reduction in runtime from exponential to quadratic makes the dp solution far more practical, especially for larger input strings. Ultimately, this approach balances efficiency and resource usage to provide an optimal solution for determining whether the string can be converted into a valid palindrome within the given constraints. One common mistake when solving this problem is not accounting for edge cases like an empty string or a single character. For instance, an empty string or a string with just one character is always a valid palindrome because there's nothing to remove, so the function should return true as long as k is non-negative. Another misunderstanding arises with the removal count, k. It's important to remember that k specifically refers to the number of character removals allowed, not insertions or replacements. Misinterpreting this can lead to incorrect logic in your solution. Efficiency is another critical aspect. Relying on a naive recursive approach without memoization can cause your solution to become exponentially slow due to redundant calculations. To avoid this, always use memoization or dynamic programming. Lastly, initializing the base cases correctly in a dynamic programming solution is crucial. For example, substrings of length 1 or 0 don't require any removals to be palindromes, and failing to handle these cases properly can lead to inaccuracies in the results. Off-by-one errors in substring indexing are another frequent source of bugs. When defining substring boundaries, it's easy to make mistakes, such as including or excluding the last character unintentionally. For instance, using s(ij) instead of s(ij plus 1) can lead to incorrect checks for palindromes. A key insight to simplify this problem is recognizing that it can be reduced to finding the longest palindromic subsequence, or LPS. The relationship is straightforward. The minimum number of removals needed to make the string a palindrome is equal to the string's length minus the LPS length. This insight allows us to solve the problem efficiently using dynamic programming. Specifically, you can use a 2D dp table where dp, ij, represents the LPS length within the substring s(ij plus 1). The transitions involve comparing characters at indices I and j. Alternatively, for small values of k, you could explore backtracking with pruning, but this approach won't scale well for larger inputs. During interviews, it's important to clarify input constraints, such as the maximum length of the string or the possible range of k, and to test edge cases such as when k is 0, or when the string is already a palindrome, or when no solution exists even with k removals. This problem is also closely related to a number of other problems on LeetCode. For instance, LeetCode 516, longest palindromic subsequence, is fundamental here because the LPS length directly determines the minimum number of removals required. Another related problem is LeetCode 1312, minimum insertion steps to make a string palindrome, which involves a similar concept but focuses on insertions instead of removals. There's also LeetCode 680, valid palindrome 2, a simpler variation of this problem where k is fixed at 1. This is a great starting point for understanding the basic logic behind removal-based palindrome checks. Lastly, LeetCode 5, longest palindromic substring, can help you develop an intuition for identifying and working with palindromic structures in strings, which is an essential skill for solving this and similar problems effectively. There are several approaches to solving this problem, each with its own trade-offs. A brute force approach using backtracking involves recursively trying all possible character removals and checking if the resulting string is a palindrome. While simple to implement, this method is highly inefficient with exponential time complexity. A more optimal approach is dynamic programming. By using a 2D DP table to compute the LPS length, you can derive the result as lens minus LPSs being less than or equal to k. This method is efficient in both time and space, with a time complexity of O(n) squared, and space that can be optimized to O(n). Another option is the greedy two-pointer approach, where you use 2 pointers to check if the string is a palindrome while allowing up to k mismatches. However, this method has limited use, as it's most effective when k is small or when the string is already close to being a palindrome. For larger values of k or more complex cases, it becomes inefficient. Choosing the right approach depends on the constraints and characteristics of the input. Great work! To wrap up, we reviewed how to solve valid palindrome 3 using dynamic programming. This solution highlights the importance of understanding palindromic subsequences and optimizing for constraints. Don't forget to practice similar problems and apply these concepts to strengthen your skills. Thank you for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!